Tech Nuggets, IPv4 subnetting, a binary perspective. IPv4 addresses are typically expressed in two different ways: dotted decimal, which are more human readable, and binary, which is more computer readable. In binary, IPv4 addresses contain 32 bits that range from all zeros to all ones. This is referring to the global IP address space. For this nugget, we're also going to show a dotted binary form to help show the relationship between the two other forms. Converting between dotted decimal and binary forms is done 8 bits at a time. The 8-bit binary number is often referred to as an octet. Conversion from dotted binary to binary is as easy as removing the dots and spaces. Note, conversion from the binary form directly to other systems is possible but very unconventional. Note the differences between the dotted decimal form and the decimal form of the number. Through the IP addressing process, it's going to be very handy to be able to convert from 8-bit binary to decimal and back from decimal, and from decimal back to 8-bit binary. Many calculators will do this conversion for you. You just have to remember to convert it 8 bits at a time. Here are two series of numbers that you will see often in IP addressing and are critical to converting between binary and decimal. They can be memorized, or they can also be easily derived by hand, for example, during a test that doesn't allow outside materials. Let's look at the conversion of the 200 octet from our example IP address 192.0.2.200. The process is as follows. Compare the number to be converted, 200 in this case, to the first place value, 128. If the number is larger, put a 1 in the resulting number in that place. Subtract the place value from the number to be converted. This leaves us 72 to be carried on to the next step of the algorithm. We're going to repeat this process. So again, 72 is greater than 64, so we'll place a 1 in the 64th column and subtract that value, leaving us 8. Moving on to the next place value, 8 is not greater than 32, so we put a 0 in the 32nd column and continue on with our 8 value. We'll repeat that same process for 16, but with 8 we reach a value where we need the 8 again, so we put a 1 in the 8th column and subtract its value, and in this case we're resulting in 0. Since the remainder is 0, we'll put 0 in the remaining least significant digits. If we want to run this value in reverse and convert the binary number 11001001 back into decimal, we look at the place values, and every place we see a 1, we add those values together. So we have a 1 in the 128th column and the 64th column. We'll add those together to get 192. We have a 1 in the 8th column, and we'll add 192 and 8, and that gets us back to 200. The internet is a very large system. This makes it impractical for every machine to know where every other machine is on the network. The internet simplifies this problem with an IP addressing schema that gives a series of addresses to machines that are in the same part of the network. For example, the authorities that are responsible for managing the global address space have assigned all of the addresses that begin with 132.235 to Ohio University. Groups of addresses on the internet, like this, are known as IP networks. Subnetting is the act of dividing larger IP networks into smaller networks, and networks are sometimes called subnets in this environment. An IP network is uniquely identified by two elements of information: the network address, which represents the beginning of the IP network range, and the subnet mask, which defines the range of addresses that are part of the IP network. The subnet mask can have two different forms that represent the same information. For example, Ohio University's subnet mask is 255.255.0.0 in a dotted decimal format, and in a CIDR format, it's represented by an IP address followed by /16. So all of Ohio University's 65,000 addresses are represented by 132.235.0.0 with a subnet mask of 255.255.0.0, or simply written 132.235.0.0/16. And for reference, I've shown how these numbers are converted into their binary or dotted binary form. Here are some common subnet masks in CIDR, dotted decimal, and dotted binary forms. Moving between the dotted decimal and dotted binary is a simple decimal to binary conversion done 1 octet at a time. Notice that the CIDR notation is the count of the number of ones in the binary form of the subnet mask. For example, 255.255.255.0 is all ones in the first 3 octets, so 8 ones in the first octet, 8 more ones in the second octet, and 8 more ones in the third octet. The fourth octet is all zeros, but 8, 8, and 8 give us 20/24 for the number of ones in that particular subnet mask. Here are 3 simple cases for subnet masks. In each of these, the ones in the mask line up with the dotted decimal boundaries. With some practice, it'll be easy to see that these simple cases make it easier to do subnet addressing without having to go into the binary form. The subnet mask defines a separation within the IP address. Where the subnet mask is ones in the binary form, the corresponding bits in the IP address are part of the network portion of the address. Where the subnet mask is zeros in the corresponding bits in the IP address are part of the host portion of the address. As you can see in this example, the network portion of the IP address is defined by the subnet mask as defined by the subnet mask, remains constant for all IP addresses in the range. Each subnet contains 2 special addresses. The network address is the first address in the range and contains all zeros in the host portion of the address. The broadcast address is the last address in the range and contains all ones in the host portion of the address. These 2 addresses cannot be assigned to devices on a network. In the core of the Internet, all of Ohio University is identified by one record, 132.235.0.0/16. Once inside of the university, the range is further subnetted to satisfy the needs of the network within the university. This means that the network within the university will have IP networks that are smaller in size and will have network numbers other than 132.235.0.0. For example, part of the ITS network is 132.235.201.0/24. This process is true for larger networks as well. It is possible to set the subnet mask at any point between 0 and 32. So let's look at the following example. Let's use the host address, or an address that we know is given to a device, computer, router, etc. that is on our network. The address will be 132.235.160.250, and we're going to use an example subnet mask of /25. We're going to be asked to calculate the network address and the broadcast address that are associated with that particular address and subnet mask. The first step in this process is to convert the dotted decimal over to a binary form. We're going to use the dotted binary form again because it's easier to see the relationship back to the dotted decimal. After converting our net mask, we can see where the dividing line between the network portion and the host portion of the address is. In this case, we're identifying that with the orange outlines. Then we can copy the host portion from the IP address that we have. We'll copy that both into our value for our network address as well as the value for our broadcast address. Then we take and we put in the known values for the host portion, all zeros for the network address and all ones for the binary, or all ones in the binary for the broadcast address. We can then take those binary numbers and convert them back into their decimal form. One word of caution at this point. You will see numbers like the 128 in the last octet of the subnet mask, as well as 128 in the last octet of the network address. These two numbers are not directly correlated to each other. You may have situations where these numbers do not match even though they're the same. And you also notice that we have one of the very common numbers of 255 in the last octet of our broadcast. This is also a very common number that will be repeated, but they don't have necessarily a direct correlation with the last address every time. And in some cases, these are also usable addresses for particularly large subnet masks, especially things that are larger than, say, 24, which falls on that last dotted boundary. Since the network and broadcast address are reserved and cannot be used as hosts on the network, it's also important to consider what the usable range of addresses is. In this case, it's every address that exists between the network address and the broadcast address. In our case, range extends all the way from 129, which is a usable address, all the way to 254. This is the point where we start to look at particular conventions, and every organization is going to have a different convention. And within the ITS labs, we use the convention, at least as often as possible, to use the last usable address to be used by the router. In this case, .254, or one address right beside the broadcast address of .255.